Okay, so what we're going to do today is we are going to do everything. So we're going to take elements from problems A and from problem B and from problem C and throw it all together into big honking problems, because until now, every time we've added something together, we have added things that were conveniently exactly 90 degrees apart. I walk straight east and then I walk straight south and stuff like that, where we have these nice 90-degree angles. And that does in fact happen sometimes, but oftentimes we have things interacting at things other than 90-degree angles. So what do we do then? So that's what we're going to learn now. So first we're going to draw a nice compass. And again, just pretend this is your empty page and you're drawing in there. So, excuse me, we have all this stuff that we're going to put on here. So what we want are some random numbers. So Aaron, give me a number between 0 and 360 that's not one of your compass points. Which one? Any angle between 0 and 360 that's not one of the compass points. 263. Okay, so 263 is going to be going about this direction. 263. So give me a number between 1 and 100.
86.
86. Cassie, give me another angle.
74.
74. So 74, of course, would be going somewhere this way. Excuse me. Trey, can you give me a number between 1 and 100?
32.
32. Excuse me. Irving, can you give me another angle?
285.
285. So 285 is going to be pointing somewhere in this region. Excuse me. And Chris, can you give me a number between 1 and 100? 5. 5. Okay, so we can agree that these are pretty non-90-degree numbers. Now, this one is very close to a 180-degree angle, but it didn't turn out to be exactly 180, so that's good. So we can't just subtract from that. But what we need to do now is we need to make triangles. So I'm going to make first the blue triangle. The blue triangle is going two directions. It's going both south and west. It's going mostly west and a little bit south. Now, since the red number is also going mostly west, I'm going to draw this one going south and then west just so my triangles don't overlap so much. But it doesn't really matter. We can draw it going west and then south, or we can draw it south and west. It doesn't matter. But like I said, I'm going to draw it going south and west. So if I draw it south and west, I want to find out what this internal angle is. Now again, I know that the hypotenuse is pointing toward 263, and south is pointing toward 180. So from 180 to 263, that's a total of 83 degrees. So that angle in there becomes 83 degrees. Now the south side is the which side? Adjacent side, so we're going to use? Very good. I know it was a long weekend, but the adjacent side we always use cosine, and then we multiply by the hypotenuse, which in this case is 86. Now the west side here compared to the angle is the opposite side, so we are going to use sine of 83 times 86. Your calculator, of course, needs to be in degree. And the N doesn't stand for north, the N stands for Newton. So we find out that we're going 10.5 newtons south and we're going 85.4 newtons west. I want you to always stop and pause for a second whenever you do these triangles, because it's really easy to get confused and switch your sign for your cosine. If you get confused as to which one is which, just stop and look at the way you drew it. When we drew it this way, we were going mostly west and a little bit south. So if you look at the numbers, do the numbers tell me I'm going mostly west and a little bit south? Yeah, so you stop and check that, and then you make sure that you didn't flip your sine and cosine up. So that's pretty easy to check. So if we look at the green one's going mostly east, but a little bit north. So if I had to tail east and north, that would be going northeast. And again, I want to find out what this internal angle is. So I say, well, the green one is pointing at 74, but the east one is pointing at 90. So from 90 to 74, that's a change of 16. So inside here we have 16 degrees. And the north is the which side? This is the opposite side, so I want to use sine. And the east one, I'm going to stick up. East is adjacent, so we're going to use cosine. And again, when we double check this one, which one should be bigger? Yeah, in our triangle, clearly east was much bigger than north, and when we look at this, east ends up bigger than north, so that's good. Then we switch to the red one, and the red one's going mostly west and a little bit north. So again, if it's going northwest, make sure you break it into north and west. Sometimes people will look at a triangle like this and they'll say, okay, it's going this way and it's going this way. And that doesn't make any sense because, again, you know that the hypotenuse arrow is pointing northwest, so you can only break it into north and west. You can't break it into south and west. That wouldn't make any sense. So make sure that you draw your arrows pointing the direction that this is going, both west and north. Again, we need to find out what this internal angle is. And I know that the arrow is pointing at 285 and west is pointing at 270. So from 270 to 285 is a change of 15 degrees. So to find the west side, west of course is adjacent, so I want to use cosine of 15 times the hypotenuse of 5. And the north side is opposite. Excuse me. So the north side is going to be sine of 15 times 5. And so again, when we look at this, we said it was going more west than north, and again, our answer is bigger in the west than it is in the north. So now we have broken this up. That was step 1. Now you're saying, wow, that was a really, really long step. Luckily, that is 3/4 of the problem is step 1. But step 1 isn't hard. Step 1 just can be a little bit long. So again, you want to make a triangle. You want to make sure that you're drawing in the 2 directions that the arrow is pointing. And you want to use cosine for the adjacent side and sine for the opposite side. Once you have that done, once we have done that, the reason we have done this is now we have a bunch of numbers that are all going either north and south or east and west. Are those easier to add? Yes. So next we are going to make a little chart, and our little chart is going to say north and east. Now if I take my green numbers here, where am I going to put the 30.8? In the east column. Where am I going to put the 8.8? In the north column. Then I'm going to look at my blue numbers, and I'm going to say, wait a minute, I don't have a spot to put south or west. So if I don't have do I need a new chart? No. I can use this chart, because I know south is opposite of north. How do we put it in opposite? Negative. South is just negative north. So south I'm going to stick in negative 10.5 in the north column. And west I'm going to put 85.4 as negative east. So negative 85.4. Then we go to the red one. And in the red one we have west, so that's going to go in as negative east. And north is going to go in as north. So now we want to just add them all up. So I'm taking all my norths and subtracting my souths, all my east and subtracting my west. So that's easy because they're all in a nice straight line. 8.8 minus 10.5 plus 4.3 gives me negative 0.4. Then I have 30.8 minus 85.4 minus 4.8. I get negative 59.4. Now, if I got negative 4 in the north column, that's really going, okay, but that negative just told me it was going opposite of north, so it's really 0.4 newtons south. And when I got a negative number in the east column, that says I'm really going 59.4 newtons pulling west. And so this will always work out. If I would have gotten a positive answer in the north column, then this word would have been north. And if I would have gotten a positive in the east column, then this number or this word would have been east. And so it would have worked out the same way. So if you get a negative up here, it just tells you you're going the opposite of whatever is at the heading. So that becomes real easy. So now we go back to what we learned in part A. If you remember way back in part A, excuse me, we now have 2 numbers, and these 2 numbers in the box there are how far apart? One's south and one's west. So now they're exactly 90 degrees apart. Is there any way we're going to get two answers here that are not 90 degrees apart? No, because we're always going to get either north or south on the left, or we're always going to get either east or west on the right, and north and south and east and west, and it's always going to be at 90. So now I know how to deal with these. I just have to hedge a tail. Since the west is bigger, we're going to go west first. So I'm going to draw west, and that's going to be 59.4. And then I'm going to go south, and that's going to be just 0.4. And so I'm going to look for my R. And again, how do we find our R? That's Pythagorean theorem. So we're going to have 59.4 plus 0.4 equals. And we have to square root that. I don't have a noise for that. 59.4 newtons. So we have the magnitude half. Now we need to find the direction half. So again, the direction half, we always look for the starting point angle. This was my starting angle. So what did we do to find this? If we know that the 0.4 is opposite and the 59 is adjacent, we're stuck using tangent, and since we're looking for the angle, we do tangent to the -1. And again, the opposite goes on top. So 0.4 over 59.4. I'm thinking this is going to be a small number. And we're going to pretend that rounds off to 1 degree. Just because it's going to be easier for what we're talking about here. So, I would of course round down, but we're going to pretend that rounds up to 1 degree. Now, if that's 1 degree, that means that R is 1 degree lower than where 59 was pointing. 59 was pointing west, which is 270. So if I drop down a degree, this is going to be at 269. And again, I'm just pretending that rounds up to 1 so that I can show you what that step is. Because when you use random numbers like we got, you never know what you're going to get for these answers. Now, if I asked what is the resultant force between these three, we would stop right now. But if I asked what fourth force is going to balance these three out, then I'd say I have to change my resultant to an equilibrant. And I say, if those three together are pulling at 59.4, then I would want to pull at 59.4. And if they're pulling at 269, I want to pull the opposite way. And how many degrees is that opposite?
89.
How many degrees is it in a straight line?
180.
180. So did I get 180 bigger or 180 smaller?
Smaller.
180 smaller, so that's going to give me 89 degrees. So I told you that first step was the longest. It wasn't hard, but it was long. And then we just stick them in the chart, add them down, figure out what direction they're really going, head to tail those two, find the R really easy. That's an at symbol. Is that better? Okay. Yay, team. So that is how you handle ones that are more complicated, the ones that don't have 90-degree angles. What if we only had 2 forces to begin with? Then step 1 would have been shorter. Instead of having 3 sections, it would have only had 2 sections. But it still works the same kind of way. And again, if I'm just looking for a resultant, then I stop at the R step, and I don't go down to the E step. That's all there is to it. It's really not that bad. It's taking the easiest part that we learned in part C, and the easiest part we learned in part A, and the super duper easy part, we learned in part B, so it kind of combines everything, which is why we're learning it one step at a time. So when I show you this, you